Today we're going to talk about another area of quantum mechanics, or the emergence of quantum mechanics, and that's a model of the atom called the Bohr model. Named after physicist Niels Bohr, who developed it. This is an example of an early quantum mechanical model, and we call it a quantum mechanical model because it introduced the idea of quantization. And by that, we mean that just as Planck had introduced quantization of the allowed energies of photons in electromagnetic radiation, and that was carried forward by Einstein, Bohr introduced the idea of quantization, or certain allowed values for the allowed radii of orbits in the atom, and in doing so, created a model which could describe a large amount of experimental data very well. So when something takes on certain discrete values instead of any value amongst the real numbers, we say that value is quantized or discretized. Another very interesting feature of the Bohr model is that it made a connection between the quantum mechanical world and the classical world. In other words, Bohr was able to describe under what circumstances physical models should be described with Planck's constant and quantization, and when that carried over to the classical limit described by Newtonian or mechanics or Maxwell's electrodynamics. The other thing that was very important about Bohr's model is that it attempted to make an empirical description to several important pieces of data known at the time of his original paper, which is 1913. And the specific pieces of data that he was trying to accommodate were, first of all, the characteristic emission of light of certain colors, from different atomic species. And by this I mean that certain atoms, like neon, could glow in certain colors if you heated them up, or other atomic species like copper tends to emit in the blue if you heat up a sample of copper, or other samples like sodium would tend to emit in the yellow. And not only did these different atomic species emit in different colors, but the wavelengths at which they would emit were very, very sharp, namely that there were specific wavelengths that were being emitted. So this was seen to be something quite characteristic of the atom, and again had a sort of discrete nature to it, because only certain wavelengths were known to emit. The other piece of experimental data that Bohr's model attempted to cover was Rutherford's discovery of the nucleus. And Thomson's electron. In 1897, Thomson had discovered the electron. It was quite a matter of conjecture as to what it was that made the atom neutral. Was it that this negative electron was swimming around in a soup of positive charge of some other sort, or was it in fact, as Rutherford discovered, a heavy, dense nucleus at the center, which the electrons were orbiting around. Well, the notion that the electrons are orbiting around the nucleus was in fact the model developed by Bohr. In fact, the concept of substructure inside the atom, little bits and pieces of which the atom is made, should have already been on people's minds because of this characteristic emission of light at various colors from atomic species. Even to a classical physicist, light is something that takes place, or electromagnetic radiation is something that takes place as a result of vibrations or characteristic frequencies of vibration of something like a charge, a moving charge. And so the notion that light was being emitted from atoms, which at that point were thought to be fundamental particles back in the 1880s or before, should have been some hint that atoms had some structure inside that could be vibrating in the first place. So why don't we first talk about some of this data that gave Bohr his first hints around which he made or constructed his model, and then we can talk more about the Bohr model itself.